Okay, let's talk about limits. Limits are a central idea to calculus. They're a foundational idea. They're how we get to the concepts of derivative and integral. So we're talking about the limits of a function. And so let's give you the definition to start. The limit of a function is the value it is approaching as you approach the point. So let's say you have a particular value you're putting into a function, right? So x equals 3. You plug in the value of x equals 3, the value of the function comes out as some other value. So if we're looking at this graph here, at x equals 3, we're at like 0.01 or something like that, right? So that's the value of the function at that point. The limit of a function at that point is what that function is approaching as you get closer and closer to the point, which honestly sounds like the same thing, but it is something different. So you can approach the limit from either side. You can either be saying, okay, and getting closer and closer to x equals 3. Let me go to my laser pointer tool. I like that one better. So let's say I'm approaching it from the lower end. So I'm starting at 2. I'm up here, and I'm approaching x equals 3. I'm getting closer and closer to this point. Or now maybe I'm coming from 4, and so now I'm starting down here, and I'm approaching 3 from the positive side, and I'm getting closer and closer to this point. And no matter which way you go, you get here. And so the value of the function and the limit of the function from both sides in this case is the same point. Okay. Now, we've talked about piecewise functions, and in the previous lecture, when you have a hole in a graph, when there's a point not there. So let's come up to this function, this specific function here. It's sine of x divided by x, okay? And so sine of x, we certainly know what that graph looks like, and x, we would know what that graph looks like. The problem with this function, if you want to call it a problem, is that you can't plug in x equals 0, right? You can't plug in x equals 0 because it's a dividing by 0, which would essentially be an infinite answer. But also sine of x at 0 is 0. So you get this 0 over 0 thing. That's a common result in as we get to the concept of a derivative. What is 0 over 0? Right? You have 0, but you're dividing it into 0 pieces. Is it 0? Is it infinity? And the answer is it could be anywhere in between. And we see that in this graph here in terms of the limit. Because there's a hole in the graph, we can't plug in x equals 0. We can't divide by 0. However, you can approach that point from either side of the graph. And so the graph is showing you what you get when you do sine x divided by x. And as you get closer and closer to x equals 0, you're getting closer and closer to the value of 1. So even though the value of the function at 0 is undefined, there is a limit to this function. It's approaching the value of y equals 1. Okay, and the table here shows you coming from either direction, coming from the negative side, getting closer and closer to 0, or coming from the positive side, getting closer and closer to 0. All right, so we're getting closer and closer to this point. So the limit of a function is distinct from the value of the function at that point. They can be different answer. We can have an undefined function at a point, but it does have a limit there, okay? Which I know at this point sounds like a really abstract concept, but trust me, it's an important one to understand. Okay, so here are 3 different functions where we can think about the limits at critical points. So here at x equals 2, again, same issue where you can't divide by 0. But also the numerator at that point, if I plugged in x equals 2, 2 squared is 4, 4 minus 4, so we have 0 over 0 again. So there's a hole in this graph, and so the function is undefined at this point. However, you can approach this from either side and get to the same limiting value. This piecewise function here also has a hole in it, but it's discontinuous. So the function is down here, then it jumps to up here. So this illustrates that the limit of a function can depend on which direction you're coming from. If you're coming from the positive side, you end up here. If you're coming from the negative side, you come over here. So this is a situation where the limit is different whether you're approaching from the left or the right. So limits are directional, right? You talk about the limit approaching the point from a certain direction. If you don't specify which direction, then that presumes you could come from either direction. So in this case, it's the same answer, whichever direction you go. This one's a little bit different, right? Because we have a function that blows up when x is equal to 2. We're dividing by 0. It's not 0 over 0, like these other two were, but it's 1 divided by 0, which goes to infinity, so the function is undefined at this point. It's this sort of this unlimited growth from either direction. And so there is no limit to this function. It's limitless. It keeps going up and up and up and up and up as close you can get to x equals 2. So it's limitless from both sides. All right. So here is, I might have made this point clearly enough already, but here's two functions that are basically the same thing, except this one has a hole in it. So they look different, x plus 1 and then x squared minus 1 over x minus 1. But if you think about the x squared minus 1, let's see if I can write on here. So let's say x, that might test my writing with the mouse skills, x squared minus 1. You could factor this, and you could factor this as x squared. Sorry, this is probably excruciating. Oh, I'll delete that. You can factor this as x plus 1 times x minus 1. Ooh, yeah, I need to have an iPad or something so I can write on that rather than writing with my mouse. Okay, so the point I made there, very terribly, is x squared minus 1 is the same thing as x plus 1 times x minus 1. So if you want to see that, just do the factorization. X times x is x squared. Then you have an x times a minus 1, and x times a plus 1. Those cancel. And then you have a 1 times a minus 1, which is just the minus 1. So these two things are the same. If you put that in the numerator here, you'd say, okay, I'll have x plus 1, x minus 1. I just cancel the x minus 1s, and I just get what you had over here, x plus 1. So that's why these functions look the same, but they are different in the sense that you can't do this division at x equals 1. You can't do the division at x equals 1. So these two functions are the same at every point except for x equals 1, and this one has a hole in it at x equals 1. So these are two functions where they have the same values at every point except for 1, but they have the same limit throughout, right? So the limit at x equals 1 is the same in this function as it is in this function. And here we have just the 1 over x. We started out with the example we had with sine x over x. But this is 1 over x, and 1 over x blows up at x equals 0. It goes to infinity on the positive side, and then it also goes to infinity on the negative side. And so this is a case where we have an undefined limit as you approach from either direction. This one, some people would write like the limit as x goes to 0 is infinity. Technically, that limit is undefined, right? Infinity is not a number, it's a concept. It's like that it goes up and up and up and up and up forever. Okay, so let's end our introduction to limits with a particularly strange looking limit. So we've seen limits that are undefined and limits that are different from either side. This is a case where the limit doesn't actually exist. And the function we have here looks fairly simple. It's just sine of 1 over x. Now sine of x is just an oscillating function. We know what that looks like. 1 over x we've just seen blows up at x equals 0. So what makes sine of 1 over x particularly strange at x equals 0? Well, think about what happens as x gets closer and closer to 0. This number is getting smaller and smaller, so the argument of the function, what's in here, is getting bigger and bigger and bigger. Now what does the sine function do as x gets bigger and bigger and bigger? As its argument, sorry, gets bigger and bigger. Well, it just oscillates. It goes up and down, up and down, up and down, up and down. So that pattern never asymptotes to any value. It never reaches a steady state. It just goes up and down and up and down between -1 and 1. So if I'm at 1 trillion or 1,000,000,005, the value could be anywhere between -1 and 1. And if I add a trillion to that, I could be anywhere between -1 and 1. So it's not approaching any value. It does not have a limit. The limit does not exist as x gets as the argument of the sine function gets really, really big. So the argument of this sine function is 1 over x, so that problem happens when x gets really, really close to 0. So let's look down here. We're getting closer and closer to 0 from the negative side, closer and closer to 0 from the positive side. As you go down the list, whatever happens on the left, it's the negative of that on the right. So it's positive 0.5 here, negative 0.5, positive 0.8, negative 0.8. So they're going to be opposites. So first thought is, all right, it's going to have a different left-sided limit versus right-sided limit. But then what is it doing as you're getting closer and closer to 0? It's just oscillating between -1 and 1. So it's not approaching any particular value. Now this graph looks like I should have zoomed in. Right? I should have zoomed in on this so I can actually see what's happening at x equals 0, so I can see, like in previous slides, we could see what was going on with the picture at that point. But what's happening with this function is that as you get closer and closer to 0, the wiggles just get closer and closer together. And so as you're approaching 0, it's like going to infinity in the regular old sine function. So you can't. The answer is you can't. You can't zoom in on this and spread these wiggles out to see what's happening in the middle. It goes on forever, and no matter what you change the scale to, it will look like this. And you won't be able to see what's happening at the 0 point because that limit does not exist. So ending here with a very weird function. Hopefully you get the idea of a limit. The limit is different from the value of a function. It is where the function is heading towards. Sometimes the limit does not exist, like in this case. Sometimes it's undefined because the function is blowing up. It's going to infinity. So it's sort of unlimited in that case. And then sometimes it approaches a value. Like we could ask about the limit of this function as x gets closer to 0.4, or as x approaches 0.4, and we would say, okay, it's here. Right? In that case, it's the same as the value of the function. All right, I think that's all I needed to say about limits. Hopefully you're getting the concept in principle, and then when we talk about derivatives next week, we will apply this, and you'll see why we had to learn about limits.